Well, good evening, everyone. I think we've reached critical mass of the register, so we'll probably have a few people join us, but we wanted to go ahead and get started. Welcome to the second class in our Home Energy in Alaska series, the cold climate, ductless heat pumps, and energy efficiency basics. Just so you know, we do have a couple more seminars coming up on the topics of heat pumps for realtors and solar PV for homeowners. You can visit the website at cchrc.org for more information and to sign up if you're interested in those. My name is Mindy O'Neill. I'm the Executive Director of the Cold Climate Housing Research Center. And we wanted to take a moment right now to introduce our sponsors, GVEA, Alaska Housing Finance Corporation, Southeast Conference, and Solarized Fairbanks. Because of the generous support from our sponsors, all our classes are provided free of charge. And when applicable, we offer CEU credits. And tonight is one of those nights that we have those. Special thanks also to the teams who helped put this series together. Information Insights, tonight we have Carrie Nelson with us, NREL, and Alaska Heat Smart. We'd like to take a brief moment to tell you about a new initiative that will help fund energy upgrades for nonprofits in the state called Solarize Bright. As a pilot project launched from the Solarized Fairbanks effort, Solarize Bright helps raise money for nonprofit organizations to upgrade their buildings to be more energy efficient. If you appreciate these classes and would like to help see nonprofits become more energy efficient, please consider donating to Solar Bright today. And if you'd like more information, an official launch will be hosted virtually this Thursday from 5:30 to 6:30, or you can just scan the code on this slide. Now I'd like to take a few minutes for some housekeeping. First, tonight's presentation is loaded with some great information. We'll be holding all questions until the break. And if there's time to go through that, depending on our time level, then we can address some questions and we'll have time for questions at the end. We do want to value your time tonight and end on time. So if we don't get to your question, we'll provide them to the speaker and they can respond individually. Just a few notes on Zoom etiquette. We're all pretty familiar with this by now, let's hope. But for this seminar, we appreciate you keeping yourself on mute. And if you go off mute, our instructors will go ahead and mute your sound. Throughout the event, we'll have a poll here in just a second and an exit poll. Please participate in them. It's really valuable information for us to know who is taking the classes and how valuable they were to you. For those of you who registered for CEU credits, it's important to stay engaged and answer any questions, but most importantly, that your name matches the registered name that you put in for the CEU credit, so we can match those up and get your certificate off to you. So you can see there was an intro poll that was just brought up as I introduce our speakers for this evening. Please participate in the entry poll that's launched now. So first, it's my pleasure to introduce Ness Stevens. Ness began working for CCHRC as an intern in 2010. She received a BS in physics from Texas A&M in 2004, and then spent 2 years serving as a Peace Corps volunteer in Tanzania before moving to Fairbanks. In Alaska, she earned an MS in physics from UAF while working as a teaching assistant for a distance education physics course. Her professional interests include all types of science education, sustainable housing, and green energy. And in her spare time, Ness enjoys paddling during the summer, skiing during the winter, and cycling year-round. Our second presenter this evening is Conor Dennehy. Conor is a researcher at NREL's Cold Climate Housing Research Center, where he collaborates on high-performance residential construction projects through energy analysis, mechanical design, and workforce development. His research efforts focus on cold climate appropriate building technologies, especially HVAC technologies. With that, it is my pleasure to introduce Ness and Conor. Go ahead and take it away. Thanks everyone for being here tonight.
Thank you, Mindy and Carrie. So as Mindy mentioned, my name is Ness. I've been working at CCHRC since 2010, and my first project was actually about heat pumps. So it's been really neat over the past 12 years to see how far they've come. Just being more of a technology that is in Alaskan homes. Tonight, Connor and I are going to talk about a couple different aspects, mainly focusing on ductless heat pumps. There's a ductless heat pump in the picture there. That's the outdoor unit. So we'll talk a little bit about how they work, just some like background information, some things that you might want to think about if you want to install one in Alaska that, you know, might be different than something you would read online, aimed more at like the lower 48 audience. Some best practices for installation in Alaska that you'd want to consider. And then we'll do the second half of the class on energy efficiency that kind of goes hand in hand with any heating appliance here in Alaska. And we'll end with resources. So those are some big slides of list of things that you can follow up on. And on that, Carrie is going to email the PowerPoint out after class. Like, I'll provide her the latest copies. So, you know, don't feel panicked if you're like trying to write things down or anything. As long as you had an email when you registered, then you'll get a copy of the presentation afterwards. So just starting with the basics, what is a heat pump? And I'm just kind of curious too, we have like a poll of people who have maybe heard of them or even might have one too. A heat pump is a space conditioning appliance. So in Alaska, we usually use them to heat houses, but the same appliance can also cool them. So a lot of the models have an ability to run in reverse. You know, if you live someplace like Texas or Florida and you think of running it in reverse, you think of it first as an air conditioner and second as a heating appliance. But up here, they're used as heating appliances. And then if there's a hot summer day, most models have the ability to provide cooling as well. And then air source heat pumps, just like their name says, they gather heat from the outdoor air, and then they use that heat to heat your building. So I'm just curious. Oh, everyone's heard of a heat pump. All right, awesome. And then just if anyone is curious, the majority of the people that answer the poll do not have a heat pump. So pretty awesome that a couple of you guys do. So you might have to jump in at some point and tell us how you like them. So a few things specific to Alaska. You'll hear things about heat pumps being renewable appliances, and they are renewable in that they use renewable energy from the air, but they also rely on electricity. So whether or not they're entirely renewable depends on your location. You know, in Southeast Alaska, places like Juneau, Ketchikan, where you're having a lot of hydropower in your grid, you know, these things are almost entirely renewable. If you're located here in Fairbanks, or maybe like Anchorage area, we would consider this a partially renewable appliance, because while the heat that you're getting from the air outside is provided by the sun, so it's a renewable resource, the electricity from the grid is not entirely provided with renewables. And so in this case, you're part of the way there, but it's not completely renewable when you think of something like a solar PV panel, something like that. This is a graphic about how they work. And if you want to think about how they work, I always tell people think of a refrigerator, which most of us have in our houses already. Except then you have to put it in your mind backwards, because instead of taking heat from the inside of the fridge and rejecting it into your house so that the inside area stays cold, a heat pump in heating mode is doing the opposite. So it's gathering heat from the outdoor air. You can see on there the blue lines outside of the house. As refrigerant travels through those lines, it absorbs heat from the outdoor air. And we often think, you know, when you walk outside and it's 0 degrees Fahrenheit, there's not a lot of heat to work with, but in fact, there are refrigerants that have a boiling point in that range, so they can absorb heat, evaporate into a gas. That goes to the compressor, which is the biggest part of the heat pump that uses that electricity. If anybody remembers from high school physics, right? If you take a set amount of a gas and you compress it, so you increase the pressure, it also increases the temperature. And so you're taking this lower temperature refrigerant from the outdoor air, and you're using that compressor to step up the temperature to something that is high enough that it can heat your house. After the gas leaves the compressor, it goes through some more coils, which are located on the inside of your house, and a fan blows the heated air out into your home. And then the process just repeats after that. And in cooling mode, right, this would just run in reverse to where it is acting exactly like a refrigerator, gathering heat from inside your home and then, you know, rejecting it outside by going through those coils in the opposite direction. There's a few different types of heat pumps, so I just want to put that out here right at the beginning because you will hear of different kinds. So air source heat pumps that we're focusing on now, they do gather heat from the outdoor air. There's a picture there of air source heat pump outside of a house in Juneau, but there's also ground source heat pumps. And instead of having the outdoor pipes just in the air, they actually are buried for ground source heat pumps, which is a lot more efficient because the ground temperature stays more stable year round. It's also a lot more expensive and not as accessible, right, unless you have a lot of land and the right types of soil for them to put those in. So CCHRC, our building actually has a ground source heat pump in it. So they do exist in Alaska, but air source heat pumps are becoming more common. And if we do have anybody from Southeast or the Seward area, there's also seawater heat pumps where the loops are not in the ground, they're actually in the ocean. So that's just another type where you can be gathering heat from the ocean water and then using it to heat a building. So a couple things specific to cold climates here. If you're not too into math, you can just listen, but if you like visuals, we put this graph on here. One challenge that heat pumps face in Alaska, right, is their capacity gets lower as there's less heat in the outdoor air, which is a little bit inconvenient because that is exactly the time when your house is needing more heat. And so the efficiency of the heat pump and then also the amount of heat that it's able to output, you know, is dependent, of course, on how much heat it can gather from the outdoor air. I was going to use the compressor to step that up, so it can certainly go down to lower temperatures. But at the same time, the lower the temperature is, the harder that heat pump is having to work. And then, of course, that's exactly when your house is needing more heat. And then the opposite is true as well. Like as the temperature warms up, it's a lot easier for the heat pump to heat your house. At the same time, that's when your house doesn't need as much heat because it's like warmer outside. So just something to keep in mind. This is definitely something manufacturers work on. Like they want people in cold climates to buy their heat pumps. And so they have a number of different ways that they can deal with this. And they have cold climate models out there that are designed to operate at very low temperatures. But just to keep in mind this like fundamental fact about heat pumps that, you know, the colder it gets, the harder it is for them to provide heat. I'm going to switch it over to Conor.
Thanks, Ness. Hey, everybody. So building on how there's multiple types of ways to get heat for heat pumps, so whether that's from the ground, water, or the air, there's different ways to distribute that heat. And so we can think about this in a few different ways. We've got hydronic systems, ducted systems, and ductless systems. So hydronics is probably something that most people in Alaska are familiar with. That's delivering your heat via liquid. So if you see, you know, fin tube in a house, or even if you walk into a store, you see in the entry, they've got liquid lines going into a fan coil unit. That's all considered hydronics. Those tend to be one-way heat pumps more often than not. So it tends to be heat only. You really only start to get the reversible heat pumps with the ducted varieties. So the ducted varieties come in what's called a split system or a mini split system. And that really comes of, if you think about folks who've got a forced air system in their house and it's a furnace, the furnace is in a single location. When you have a heat pump, you've split it. So you've moved the compressor and the evaporator, you've separated those. And so you've got an outdoor unit and an indoor unit. That's why people call them a split system. The mini split is a smaller version of that. So it's pretty straightforward. There's some different applications for both of them. But the ductless systems come in the mini split variety. So when you hear people say mini split, more often than not, they're referring to the ductless. And when people say ductless, they're inherently referring to the mini splits. And so it kind of depends on what your house is like, will dictate how you deliver your heat. So we can go to the next one. And so kind of building on that, if we think about everything stems from your outdoor unit, and that decides how you're going to deliver your air. So it can be in your ceiling, what's called a cassette. It can be on your wall, which is called a head, or it can be a floor unit. So those also can come in a fan variety, but essentially we're using electricity with the outdoor unit, using the refrigeration cycle. We're taking advantage of the thermodynamics of that, and then we're stepping up that temperature difference with electricity in the compressor, and then we're delivering the space conditioning wherever we want it. And generally, like I said, it depends on your house, your location, and where you're at will dictate what variety you go with. And so in thinking about your house, more often than not, we're going to be focusing on the ductless mini splits throughout this presentation. And those are really great because they're small units. They can go in lots of different places, but because of that, they can't necessarily serve your entire house. So you have to think about your house in general. So kind of stepping back from the energy efficiency aspect for a second, we're assuming your house is perfectly energy efficient. It's a great candidate for heat pumps. But now we've got to think about just your floor plan in general. Since ductless mini splits aren't fully ducted to everywhere in your house, it's kind of limited where they can deliver their heat to. So if you got a bunch of hallways connected to the bedrooms and you've got a mini split that's put into your living room, it's going to be really tough for that nice warm air in the winter to get all the way to the bedrooms. And so you can solve that through multiple heads. The caveat to that being the more heads you attach to a single unit, the slightly less efficient they will become, the more complicated the install becomes, i.e. more expensive. So you can get around that by having multiple small units, but sometimes you can find yourself starting to stack up multiple units, and you may want to think about a larger central system as opposed to doing multiple mini splits in one house. So it all just kind of depends on what you're working with already. Back to you, Ness.
Yeah, thanks, Connor. So just a little bit about the numbers that are used to measure heat pumps. So if you are looking at them online, we kind of want to have a basic understanding of what those mean. Heat pumps efficiency is measured with something called coefficient of performance, which is basically the heat that goes into your house divided by the electricity that you're having to pay for. People are pretty used to seeing numbers associated with the efficiency of a combustion heating appliance, and those numbers will always be less than 100%, right? Because when you're burning the fuel, whether it's wood or fuel oil or natural gas, there's always some heat that's lost like up your chimney. And so you'll always have this number less than 100% of that efficiency. When you go to buy an appliance, it's usually marked as the AFUE. So you'll see that number. Typical heating systems, like if you think of a Toyo stove, they usually have an AFUE that's measured by a laboratory somewhere that's in the upper 80s. So like 86, 87%. When your Toyo's burning oil, 87% of the heat energy that's available in that oil is going into your house, with 13% of it like lost up the stack, because that smoke that's going up, that exhaust is carrying some heat with it. So heat pumps, for one, they're getting some energy right from the outdoor air. So that is going to boost their efficiency, quote unquote, over 100%. But at the same time, you are paying for some electricity. So anyways, this isn't expressed as a percentage. If it was, it would be more like, 300% or something. It's usually expressed just as a number that's called the coefficient of performance. And so just if you think of a toaster, also something that has electricity in and heat out, for every unit of electricity that you buy from the utility in order to run your toaster, you get 1 unit of heat into your toast, right, into your bread. So we would say that has a COP of 1, like the electricity that you buy is directly going into your bread. But for a ductless heat pump, you'll have a COP usually that's over 1. So for instance, say the COP is 3. That means that for every 1 unit of electricity that you buy in order to run that compressor and the fans, you're actually getting 3 units of heat into your house, which is a pretty good deal. And the reason for that is because those extra 2 units of heat came from the outdoor air. And so it's actually more efficient than like an electrical heating appliance. Like if you think of like the electrical space heaters that maybe you plug into the wall during the winter, just to like get some extra heat by your couch, more efficient than electric baseboard or boilers, if that's common in your community, and certainly more efficient than any kind of combustion appliance, just because we are getting that renewable heat. COP is not typically what's listed on the label. That is a number called the HSPF. COP is like an instantaneous value, and HSPF is the seasonal value. So it's kind of like the average efficiency, like over a heating season. And manufacturers only have to report one number. So this is measured in a lab by an agency that does this for all different manufacturers. So they're a neutral agency. But the big takeaway there is the higher the number is, the better the heat pump is. And so you want to look for ones that have that higher HSPF, higher COP, higher efficiency. They're better at taking heat from outdoor air, putting it into your house. Wanted to talk a little bit about defrost cycles because this is something that happens really often in Alaska. Condensation, right, is anytime that you have cool air hitting something that's hotter than it. So it's the exact same phenomenon than if you had like a glass of ice water, a glass of ice soda in the summer and you set it out, you start getting that condensation on the glass. Same thing, we have a warm house in the winter and our windows get colder because it's cold outside and we start seeing condensation on the windows. Well, the same thing happens with heat pumps on the outdoor coils because they are running that refrigerant through them. And if there's moist air that's cold on the outside, when they hit those, it condenses and then that water kind of drips down to the bottom and it forms ice. So I put this picture here. This is actually from one of the first heat pumps installed in North Pole. You can see the ice kind of at the bottom of the heat pump is going out onto the ground. And in Fairbanks, we know that once you have ice, it doesn't melt until spring. The first year that this company installed these heat pumps, they actually put them directly on the ground, like not realizing that they needed to leave space underneath for that ice to form up. And they actually broke the heat pump. So the heat pumps were sitting directly on the ground and so much condensation was happening that it just continuously built up ice underneath. And it eventually built up enough ice that it was able to tip the heat pump over and that broke the connections to it. Got there in the morning, heat pump wasn't working. They're like, okay, this is what happens when you're one of the first people to install heat pumps right in North Pole, Alaska. So since then, this is a very old picture, right? This is 10 years old. Since then, of course, Alaskans have learned that we need to lift these up off the ground in order to give that ice somewhere to go from that condensation from those defrost cycles. So defrost cycles are what happened when there's so much ice that are on the coils that the heat pump isn't operating very efficiently. So the heat pump actually temporarily reverses cycle and sends heat out there. Besides the ice buildup, the other thing that happens is it's actually stealing heat from your house in order to do this. For those that like numbers and graphs, I kind of have a graph of like the power going into a heat pump and you can see where the defrost cycle happens and you're reversing that. The power has to switch and then we reverse. Instead of it putting heat into your house, it's actually putting the heat outside in order to melt that ice. And then once the ice is melted, it can go back to normal operation. So again, I'm not trying to scare anybody, just again, trying to give you guys facts about, how heat pumps work in Alaska and some things that you might, expect. You don't want to walk outside and see ice on a heat pump that you've installed and wonder why it's there. Another thing to be aware of with heat pumps in any location is that, the number that you see on the label is not always representative of the number that you are going to get for efficiency in your exact location. And so definitely you should consider that number in your purchase, but there's other considerations that you need to think about as well. And back in 2014, CCHRC actually measured the efficiency over one winter of 3 different heat pumps. And it was really funny because we got 3 completely different results as to what the heat pumps were doing in regards to their manufacturer specs. So you can see the blue and the black dots, which are kind of in the middle of the graph, are all the efficiencies of all the days in the winter that we had this heat pump that we were measuring. First thing you can see is that same trend line we talked about at the beginning. The higher the outdoor temperature got. So the further right you go on the graph, the higher the COP gets. So the higher up you're going. And you can see this heat pump was actually doing really well, right? Like when it was 40 degrees outside, it was getting those COPs of 3. So, you know, the homeowner was paying for 1 unit of electricity. They were getting 3 units of heat. The blue square right in the middle of them is what the manufacturer spec is. It's only reported at 1 number, and this manufacturer reported it for, you know, whatever that is, 44 degrees. And the COP that was measured in that guy's house, like it was directly in line with what that manufacturer had measured in the lab. Then we'll go to the turquoise and pink dots, which are the ones at the bottom. The manufacturer specification for that one, you know, it gave one that's like right there about 15 degrees is that turquoise star. And you can see that most of those dots fall below that. So this, you know, same heat pump that, you know, was measured in the lab, once it was installed in somebody's house, you know, it didn't actually perform as well as, you know, the number indicated that it would have. And then we have the last case scenario, the green and the red there. The manufacturer's spec is the red square. It says, okay, when it's, you know, 47 degrees, it's going to have a COP of 4. And well, this heat pump had COPs of up to 6, which is incredible. So, you know, it went the other way. Like, you know, when they bought it and they saw this number, this is how we can expect it to perform. And then it ended up performing considerably above that. The reasons that this happens, you know, part of it is related to installation. Part of it is how you're running the heat pump. You know, is it in a situation where it's on all the time, you know, constantly running, constantly trying to heat a building, or is it more in a situation where it's just supplementing heat? And unfortunately, there's not great guidance about this. It's just something that you need to be aware of, talk to, you know, an installer about when you purchase the heat pump. Make sure it's the one that is going to work best in your house. I'm going to pass to Conor here to end with some advantages and disadvantages.
Thanks, Ness. So some of the potential advantages for heat pumps, specifically the ductless variety that we're kind of focusing on today, has potential to reduce energy costs. Like Ness has just mentioned over the past few slides, it kind of depends on where you live, how much your electricity costs, and what your house is like. If you have all 3 of those working against you, a heat pump is not going to save you energy or save you money. If you have a really well insulated house, very airtight and all of that, and still have a kind of, you know, high electricity rate, you might be able to save total energy. You may not necessarily save money. So it kind of depends on, of those 3 things, how many of each of those do you have? If you've got all 3, it's definitely a no-brainer. Heat pumps are going to be great for you. If you're missing one leg of that stool, whether it be cost, climate, or cost, or energy use, then it takes a little bit of thinking to figure out whether it's going to work for you. You'll find we say that a lot here, and a lot of people you'll encounter will say that with heat pumps. When it comes to, are they right for you? It depends. It depends on the homeowner's behavior, and it depends on the house. So on paper, it can be a good fit, but there's always nuance to it. And anybody who's going to tell you whether it's a good fit or a bad fit without having evaluated your house or your needs, there needs to be a little bit more detail before you get to that final answer. And so as Ness mentioned, you know, there's the ability to have partially renewable heat. Again, that depends on where you live, what the grid mix is like for your power plants. But as long as the temperature is in your favor, then you can continue heating or continue cooling for as long as you have the ability. There is no on-site combustion with this, so this is you know, an advantage. You don't have to worry about exhausting into, you know, alleyways or near your neighbors or anything like that. You don't have to worry about having fuel oil, you know, delivered onto site. That comes with, you know, its own advantages or disadvantages, namely kind of price fluctuations. So you're pretty well aware of what you're paying for electricity. They don't really change it that often, maybe once a year, twice a year, once every couple of years, but fuel prices tend to be a lot more volatile. When it's really expensive, people will even go so far as to steal it out of your tank. And then you don't have to worry about topping it off at the beginning of the heating season. Electricity is kind of, you know, it's already hooked up to your home. You're good to go for there. And so in thinking about all of that, it can be pretty low maintenance. So for a ductless mini split, we've got the outdoor unit and we've got the indoor unit. The indoor unit has 2 filters in it. And basically, if you keep track of those filters, the unit will continue to run smoothly. It's very low maintenance. You don't have to do very much for it at all once it's installed. You do get the ability to cool in the summer, so it's not that big of a need up here in Alaska, but there are a few different days that might require it. I know up here in Fairbanks, sometimes we'll be in the middle of summer. It'll be both hot and smoky from wildfires, and so that's a good time to close all the windows and turn on the heat pump and get some air conditioning going. And then, as with most modern appliances, you've got the ability to program some things and use some remote controls or some wired thermostats. You've got a little bit of variety in how you want to actually control this thing. All right, so on to the disadvantages. So you potentially have the need for a backup heating appliance, and that can depend on it's because of where you live or it's because your house may not be the most energy efficient it could be. So just being aware that you don't necessarily want to get rid of the current heating appliance you have if you get a heat pump. So if you get a heat pump, hold on to that other one. Make sure the first winter works out for you, and then you can start thinking about getting rid of that one, replacing it, or supplementing it with something else. And so the need for that backup heating comes from the fact that there is a temperature where it will cease to be very functional for you. So there's 2 points for that. There can be a temperature where it doesn't make economic sense for you to run it anymore, but it'll still put out enough heat that'll keep your house warm. And then there's ultimately a temperature where, as it gets colder, the ability for that heat pump to extract heat from the outside air just gets to a point to where its capacity cannot keep up with the load in your house. Because it's an appliance that depends on electricity, if you have a power outage in the middle of winter, then you're kind of stuck from that standpoint. And because they're really efficient with their power use, but they require a lot of instantaneous power, it's not something that you can grab a little 1,000-watt generator and get going like you could with a Toyo stove or something like that. You have to have a lot of power to be able to use it. Noise is something that people tend to think is a problem, and they associate with older heat pumps. As technologies have advanced and heat pumps work at colder and colder temperatures, it's because they've made a lot of progress with the compressors, with including DC power and inverter compressors. And so because of that, they can be extremely quiet. However, when something goes wrong, if a fan or something is breaking outside, it will sound like somebody's putting a stick through bicycle spokes. And so if you're right next to your neighbors, that might be a problem. And there is a little bit of a learning curve to them, just understanding that when you turn it on, it's not like a traditional system to where you fire up your Toyo and it's blasting heat in your house within a couple minutes, and it's very hot, and it'll stay that hot through the entirety of its burn cycle. Heat pumps are a little bit slower to ramp up. They take a little bit longer, and some people may get a little bit frustrated with that. So they came home, their house is colder than they want, and 20 minutes go by, they really want it to be warmer, so they'll start hammering on the thermostat to raise it. So it's not really something you do with heat pumps. And then all of that being said is you got to be prepared for how it's going to go in your house. So you kind of have to have a strategy to how you're going to work with that cutoff temperature. Is it just you have a calendar reminder? Are you going to automate it somehow? So you can do it as low tech or as high tech as you want that to be, but it is something to think about. All right, so here's some resources. And as Ness mentioned at the beginning, I think Carrie as well, that we will be, wait, I'm on the wrong, no, I am on the right one. We will be sharing this, so all of these links will be available to you once this gets posted. But we do have some great in-state resources, as well as relying on some other cold states down in lower 48 that have been kind of making progress on heat pumps for a little bit ahead of us. So we've got Alaska Heat Smart in Juneau, so definitely want to give them a shout out for doing a lot of work down there. You should definitely visit their website and contact them. They're a great resource. Here in Fairbanks, we've got CCHRC. We've done a lot of work on cold climate air source heat pumps over the years. So feel free to visit the website, download some reports, reach out if you have any questions. There is a mini split heat pump calculator, because a lot of everything we've said is it depends. So it depends on how much it's going to cost what your house is like and all of that. And so you can take some generic numbers and put them into a calculator and start to begin to make a little bit more of an informed decision on whether this is a good fit for you. And so moving out of Alaska, we've got the Northeast Energy Efficiency Partnership. They've been working for a long time with manufacturers and the Department of Energy and other interested stakeholders on developing a heat pump list that qualify for a cold climate standard. So if you go to their list, there's a good chance that it's going to be more likely to work better in cold climates, because not all heat pumps are appropriate for cold climates. Likewise, we've got Resources Canada. They've got a similar style of a sizing and selection tool for air source heat pumps. So all of this is trying to hone in on how does your house perform? What is the potential for a heat pump as it gets incorporated into your house? And then we've got a few local in-state resources. This is meant to be a really cursory overview of heat pumps in general, just to kind of increase your familiarity with them. But there's more opportunity to take more detailed classes on kind of the design aspect of them. We can go to the next one.
Okay, I was trying. It took me a couple clicks. Did it switch?
Yeah, it looks like
Okay.
a switch for me.
Did not switch with my keyboard, but it worked with mouse. Okay.
All right. So we've got a resource that we want to share. It's from the Efficiency Main Installation Requirement Checklist. So as I mentioned, there's some colder states down lower 48 that they've been making progress for a few years on getting heat pumps out into the world. And so they've got a kind of, it's not a detailed heat load analysis that you'd really need to be 100% confident in how this is going to work out for your house, but there are some just kind of general checklist items to figure out if this is appropriate for your house, and then as it's going there to make sure you're setting yourself up for success. And so most of these are kind of practical aspects of, you don't want to put the outdoor unit directly on the ground. As Ness talked about, there's condensate that will build up ice. And then likewise, we've got snow that falls. So if you live in an area that's got pretty high snowfall, that 18 inches is really meant to be a snow height. So if you're somewhere in the mountains and you get more than that, you may want to consider attaching it to the side of the house. But otherwise, they come with stands. You can purchase accessory stands, but the idea is you got to keep it away from obstructions. And so with that in mind, you want to keep it out of the way of traffic. You don't want to put it right next to your front door. You kind of want to find a quiet side of your house, something that's not necessarily going to be an eyesore for you or your neighbors, or that's going to get in the way of anything. In the winter, as it goes through the frost, it will create condensate and ice. So you just want to be aware of that. You don't want to create a tripping or slipping hazard for anybody. And then as you're thinking about where you're going to put it, in regards to all of that, you just want to make sure, maybe when the snow slides off your roof in the spring, it's not going to take out your heat pump. So you just got to be really conscious of where it goes. You've got between the indoor unit and the outdoor unit, you can generally go about 25 feet apart from each other. So you do have some flexibility, but at the end of the day, you've got to think about the kind of hazards around your house. All right, and so kind of building on those practical recommendations on figuring out whether it's a good fit in your house and best practices for the installs, you just want to use potentially this tool and figure out, okay, is my house even a good candidate for this? And as with most renewable technologies, so whether it's solar, photovoltaics, or anything else, we generally advocate a building efficiency approach first. And so all about figuring out how your house is performing. We figure out the design load. So the same house that's built in Fairbanks, Juneau, or Anchorage is going to have different design loads. Even if it's the same architectural specs, it's going to perform differently in different climates. And so assuming we've got an efficient building, we've got a design load that's within the manufacturer specs of what the heat pump can deliver. Now we want to think about where is this going to go. And so generally with the ductless mini splits, you want to put them in as open of an area as possible, and then try to maximize airflow between that space and other spaces. So if you have a bunch of bedrooms around a large central space, that can work out. Keep the bedroom doors open for as long as possible until people go to sleep. Maybe you install transfer grills between the bedrooms and the main spaces, or you utilize ceiling fans. It's all about trying to mix the air throughout the house. And then, as I mentioned on the last slide, we want to make sure that the outdoor unit is protected from all the outdoor hazards. And as with anything, you just got to maintain the appliance, clean your filters, keep an eye on it, kick the tires before you turn it on for the winter. Don't expect it to sit around for a long time and just magically fire up. So always do your due diligence on learning how your appliances work in your house. All right, I think that's it for that one.
Yeah, so that is it for our heat pumps, and we do have a short break. But if I did not open the chat, so, and then I shared my PowerPoint, so I can't see anything except the PowerPoint. If there are questions, we could do those for like 15 minutes and then take the break at the half point. But I don't, if no one has questions, we can also.
There are some questions. Funnily enough, it looks like we've got a couple questions about air to water heat pumps and heat pump water heaters. So we focused most of our conversations today on ductless mini splits. So those are just pure space conditioning appliances. So heating or cooling, as I mentioned. When it comes to hydronics, which is something we didn't focus on, heat pumps are great. They can take advantage of an amazing thermodynamic cycle with the power of refrigerants, but there is a limit to how much heat you can get out of that. And so when it comes to air to water systems, so you're thinking about replacing a boiler, replacing something that is delivering heat to your house through a liquid system, heat pumps only make a liquid so hot, whereas most fossil fuel appliances, they can just crank away and make really hot liquid. And so most fin tube systems tend to run really hot, and so that'd be along the lines of like 180 degrees Fahrenheit or something like that. A heat pump will struggle to put out that temperature. In fact, it won't. So it's not a good one-to-one swap for that. If you want to consider taking the fin tube out and swapping to a radiant style system, not necessarily in floor, now you're in the feasibility of potentially doing that retrofit, but you've definitely changed the cost dynamics of what you're doing. So it really depends on your goal and how you set about to do it. If you've already got a radiant system, you've got in-floor heat, now you're talking about the potential of being able to do a one-to-one swap of taking your existing appliance and putting in an air-to-water heat pump. So that's kind of a little bit of the logistics of that. And then comments on heat pump water heaters. They're also great appliances. If anybody's not familiar with them, just think about an electric resistance water heater and then add about 24 inches to the top of it, and you've got a heat pump water heater. So what they did was they took that outdoor unit that we've been talking about today and they crammed it on top of the water heater. So it's pretty impressive what they've been able to put on there. They're really efficient and really affordable. They're something that has, I think within the past 3 years, kind of really taken a foothold in the marketplace. You do want to be aware that they put out cold air into your house. So in the winter, that's kind of a parasitic heat load for you. But the nice thing about that is there's a little bit of dehumidification that happens there. So if you've got it in a basement, mech room, anywhere where there's enough airflow to for it to be able to function, that can work out for you. If you're in a small house, maybe you don't want it blowing cold air right over you as you sit down for dinner or something like that. So just as with everything, it depends on what you're working with the current house.
Yeah, I can add a little bit on the baseboards. I know that's definitely something Department of Energy and like manufacturers are considering because Northeast America, the East Coast has a lot of baseboard heating, and of course that's a big market for heat pump manufacturers, as well. But like Connor was mentioning, there's a huge cost involved to any solution. There are low temperature baseboards out there, but now you have to replace your baseboards. That's not cheap. And then there has been some talk that, maybe you could make your house efficient enough that you could use your current baseboards with a heat pump and just run them at a lower temperature. But, now you're spending a lot of money making your house more efficient. So, which that has like, a lot of other advantages, but, the bottom line there is like whatever solution you go with, it's definitely going to be more costly. If you are trying to like maintain your baseboards than it would be otherwise.
So I think that was most of questions. Maybe something about a class. But yeah, I'll kind of round that off with, it looks like there's a cost about, is a heat pump a feasible investment? So whether that's a air source, water source, whatever, if you can establish what your current house is doing, figure out how much money you're spending on energy, you begin to talk to an installer, you get some prices on what it's going to take to install the heat pump in your house, and then you can start to play with the economics of, is this a good fit for you? So it depends.
Yeah, I mean, the technology is constantly improving too. So, as you're doing your research, I would say like 10 years ago, heat pumps cut out at 0 degrees Fahrenheit, and then a couple of years later, we were hearing about models that went down to -10. Certainly when we were monitoring the efficiency of those in 2014, like, heat pumps that work down to -15 Fahrenheit were like cutting edge. And yeah, I know CCHRC is trying to evaluate a heat pump in our building this winter that operates down to -31. So, those bottom temperatures keep creeping, lower and lower down as the manufacturers like, tweak that compressor technology. So, it's an exciting thing to keep an eye on, even if it ends up not being like right for you at this time.
Yeah, it looks like we've got a question if we can share installed costs. So that's always a dangerous game to get into specific costs. We'll talk about them in kind of the broadest and simplest sense here. So if we're thinking about a ductless mini split, kind of wholesale the units somewhere in the ballpark of $1,500. It can be potentially, depending on where you're installing this, there's a certain amount of accessories that go with it. That could be up to $1,000 there. And then you're paying for a contractor to put it in. So really that depends on where you're at. We'll change that. So anywhere probably between $2,500 to $5,000. That changes. Are you doing a single interior head with a single outdoor unit? Are you doing 3 interior heads with an outdoor unit? So the price will change depending on the complexity of your install. And at the end of the day, if you can afford it and your house is a good candidate for it, then it's generally going to work out for you. But it's not something that you should necessarily dive right into with, oh, I'm about to save a ton of money with a heat pump, I should get on this or I'm going to lose money. Approach it with a good amount of due diligence.
Yeah, and I would just add to what Conor is saying that like sometimes like a hidden cost pops up. Most heat pumps, in fact, I think it's just now that they're coming out with 120 volt ones. So most operate on a 240 volt circuit. So if you don't have one of those open, most houses have them, right, to run some appliances, but if there's appliances on them, then you're looking at having to bring an electrician out to add that circuit onto your panel, which is usually not an issue. Although there are some houses that have like, really old panels that, that ends up being a pretty major cost, along the lines of like, 1,000 or a little bit over. So, it's just another thing to keep in mind is you're talking to a heat pump installer. If there's not room in the panel for them to connect a circuit for the heat pump, then, you'll have to also be hiring an electrician for them to put in that circuit. People may have heard of like the infrastructure reduction bill. Hopefully I got that right. Act. It has money for rebates for heat pumps in it. Nobody knows exactly how it's going to work. And I think everyone's crossing their fingers that manufacturers just don't raise prices like, the exact amount of the rebate. I think the latest is
I can speak to that a little bit on.
Okay, good. From DOE's end.
So the tax credit's already like live in effect, and that isn't very much money. So if you did happen to already get a heat pump installed this year, or plan on installing it this year, save your receipts. You can claim a tax credit, and that's pretty much live.
Yeah, and then
the
if people
rebates.
want
Go ahead.
information on the tax, I was just gonna say, if people want information on the tax credit, because the slide doesn't exactly say it, but the websites to look at would be that very last one, that Desire database of incentives, would give you links to that. And then Alaska Heat Smart also has information about the existing tax credit, like on their page.
Yeah, thanks for mentioning the Desire database. I think I glossed over that earlier. But the rebates that will be coming out with heat pump systems, that's coordinated between the federal government and the state government. So that's why that one will take a little bit longer to come out. So there's more money available through the rebates, but it requires a bit more of a federal infrastructure to be built out, federal state infrastructure, before people can claim that. So certainly that will make the economics better once rebates are available. Looks like we got last question here about water coolers and their similarity to heat pumps. So I'm gonna go on a limb and assume that's what I've called a swamp cooler. So that's something you'll find in drier climates. So maybe you'd be down in New Mexico, Arizona. You'll see what looks like the outdoor unit tends to be like on top of their house. And so that is, they use water. So it's just totally evaporative cooling. So there's no refrigerant involved or anything like that. And they're great if you have the climate for it. It's not really something you find for cold climates, and it's only something you find in hot and dry climates, because you really got to take advantage of the ability for water to evaporate. That's what makes heat pumps really unique, is they use refrigerant in a closed loop system. So as Ness mentioned, they have really, really low boiling points. And so, you can have a refrigerant that boils off at, say, 0 degrees Fahrenheit. And so you're able to take advantage of that phase change and utilize that heat. With water, 32 is our cutoff Fahrenheit. I think that rounds out the questions.
Yeah, I was gonna say, are we good to take a 10-minute break, or Carrie, are you keeping time, or I can keep time and I can just start talking in 10 minutes? That's fine with me.
I'm fine either way, Ness. I can also start talking
Okay.
/ yelling at you when it's time.
Yeah. All right. Well, I'll put a timer on my phone here. So
Sounds good.
10-minute break. And we do have a poll, I think, that again, it's just like Mindy was saying at the beginning, we're always trying to improve these classes, gather topics that people might be interested in. So always helps us if you answer those. So see everybody in 10 minutes. All right, everyone, this is your 1-minute warning if you have your sound on. So got a couple more minutes, but we'll start here in a sec.
Vanessa, I'm just going to flag for you, in case you don't see them, you and Connor. There's 2 questions that came through over the break in the chat. The one from Andrea and then one from Gary. Those have not been addressed yet.
Yeah, Connor and I were texting because I was trying to figure out how to get the chat open without crashing the PowerPoint off everybody's screens.
Yeah, it's
So
tricky
anyway.
when you're the one presenting. It's tricky.
Yeah. Yeah, I do know about community-based ground and seawater systems. I'm not familiar with community-based air source heat pump systems, so I'll see if Connor is, but otherwise that one we might have to pass. Connor, have you heard of that?
I usually don't see them for air source unless they're in the same building, like a multifamily building. So if you're kind of think of like the Whittier condo building, that might be a good application for people sharing a single air source heat pump system. Otherwise, you'll find ground source heat pump systems or the sea systems. Those tend to be more cost effective the more people you put on your loop, and so they'd be what's called a district system. So if you're familiar with how steam systems tend to work in like downtown areas, like downtown Fairbanks, we've got a steam system. It's called a district system. Functionally, it would be the same thing. You're just using a ground source heat pump or a seawater heat pump and then putting a bunch of customers on it.
Yeah, we'll have to look that one up. So thanks for letting us know about it.
Yeah, and then so somebody asked about costs, ballpark costs. So again, another fun loaded question to answer. It really depends on your house. Is it your primary heating appliance? How cold is it? It could be, you know, in Juneau, you could say add $10, $15 to your electric bill for having that be your primary appliance. If you were to do that in Fairbanks, it might be, you know, it's definitely going to be more expensive than that. If you think about on a per kilowatt hour basis, what we pay in Fairbanks is along the lines of like 12 to 14 cents a kilowatt hour. If you're to think about I think Ness mentioned like a Toyo stove, so it's like an 87% efficient appliance. So if you think about a gallon of fuel oil, once it gets burned, you know, loses 13% of the stack, 87% of that goes in there. That's somewhere in the ballpark of, we'll say it's 12 cents a kilowatt hour. And so here in Fairbanks, we're currently paying 25 cents a kilowatt hour for electricity. And so with the heat pump and the coefficient of performance, where you put in 1 unit of electricity and you get out multiple units of heat, you know, if we're thinking about 12 and 25, that's close to being about half. So anything below a 2 COP, which would be somewhere in the ballpark of, I don't know, the teens of Fahrenheit, so 10 to 20 degrees Fahrenheit, it would start to potentially become cost ineffective for you to be using the heat pump at those colder temperatures. So that's not to give you a general sense. So it could raise your electric bill by 15, 20%. It could raise it by 50% if you're in a small house and you use only that for the whole winter. So all of that being said is it depends on a lot of things. But hopefully that gives you a sense.
I was trying to remember because we did monitor some heat pumps in Juneau over the past winter, and I'm you know, like of course they're not in your house, they're in other people's houses. Other people have different thermostat settings, you know, but we were just trying to gather some of that, just like super generalized cost information. You know, on the coldest day in January, I think, you know, those heat pumps ended up costing the homeowners like kind of in between like $2 and $5 and that's like the coldest day, you know, kind of thing. And of course, you know, there's other months where, you know, it was way less than $1 a day to operate. Alaska Heat Smart might be a good reference, like if you follow them on social media or look on their website, because a lot of that data that we got over last winter, we're kind of making into graphics and stuff for them to distribute and use with people who call and ask questions and want like more specific ones than we can give. I'm going to go ahead and jump into efficiency. So the second half of this class is on energy efficiency. So it's more of a whole house look instead of just looking at the heating appliance. Our saying around CCHRC is that the cheapest form of energy is of course the one that you didn't have to buy to begin with. So going right from our cost discussion to you don't have to pay for the energy to begin with, all the better. There's a lot of other advantages to making your house more efficient or making it so your house uses less energy as well. Certainly if you do efficiency first, this doesn't work for everybody cost wise, but a lot of people, if they know they're going to be switching out a heating appliance, like doing some efficiency retrofits ahead of time, it does allow you to buy a smaller heating appliance, and that usually means a cheaper heating appliance. If you can get the lower capacity model because your house doesn't need as much heat. For some communities that are operating on a renewable grid, so if you are in a community with a hydropower grid, if you're able to use less electricity through efficiency, whether that's a smaller heat pump or less use of your electric space heaters or more efficient lighting that doesn't use as much electricity, it basically means there's more of that renewable electric resource for other things. So that is an issue. Like in Juneau, you don't want to have to build another hydropower plant, and so the more people that have efficient houses, the more people can convert to electric vehicles. It's less of something that we think about on the rail belt, but depending on where you're located, efficiency can really benefit the whole community. Something everywhere in Alaska thinks about is the more efficient that your house is, the longer it stays warm when you don't have power. Up here in Fairbanks, we had pretty crazy power outages last winter, just because of like freezing rain that's becoming more common, and it knocks branches onto power lines. And so there's really no good way to prevent that. And so if you are looking at a situation where you're not going to have power for a day or 2 days, then certainly having a more efficient house is pretty desirable. Buildings more durable, more comfortable, and in a lot of cases, being more efficient can actually help you have better indoor air quality. If you have a combustion appliance, you're having to run it less, so that's less just less any kind of exhaust or anything like that getting into your house. Just kind of another thing, if your building is really efficient, keep those interior surfaces and interior windows warm. You're not getting as much condensation. You're less risk of getting mold in your house or something like that. So lots of advantages to efficiency. And there's lots of different ways to achieve efficiency. It's really dependent on your house, and we'll talk a little bit later about how you can kind of narrow in on what is the best for your house. But just some common ones that we see here in Alaska that tend to have a high payback. So whatever money you put up front to do these retrofits, a lot of homeowners will see, savings on their energy bills to where they've earned that money right back in as little as, 1 year or, 3 years. So just that first one, air sealing and ventilation. If you do have a really leaky house, being able to seal up those leaks, you have to do it in correspondence with ventilation, which we'll talk about on the next slide, but controlling that airflow in and out of your house instead of just having it be uncontrolled airflow when it's -40 can really save you a lot of money. Heat rises, right? Just like think of the hot air balloon, from the pictures from New Mexico, hotter air is less dense, so up it goes. So putting insulation at the top of your house can kind of help keep that heat in. And then and similarly, like if you have a crawl space, insulating down there, preventing heat being lost to the ground can be very helpful. And that one too, especially if you're doing like vapor retarders and getting a little bit of crawl space controlled ventilation, that can help with your indoor air quality as well, like getting it to be less humid. pass to Connor to talk about a little bit of the building science nuances with some of this.
Yeah, thanks, Ness. So it's a phrase, I believe it's credited or coined by the founder of CCHRC, Jack Aber, says, build it tight, ventilate it right. It might be one of those sayings that's been around that who knows who originally said it, but he's been around and knows his stuff and said it a lot. So we'll definitely give him the credit for it. But all that being said is it means you can make a bunch of energy efficiency upgrades to your house, make some retrofits, make everything a little bit tighter, but you got to be conscious about the fact that the more you reduce air infiltration in your house, the more you actually have to intentionally introduce outdoor air into your house. Buildings do not need to breathe, you need to breathe. So as you tighten it up, you just got to make sure that you're bringing in outside air in some form or fashion. So the simplest ways to do that is with exhaust only ventilation. So that would be with the bath fans that you typically see, or if you've got a range hood, has to be vented to the outdoors. If you've got a recirculating microwave range hood or just a regular range hood that doesn't actually go to the outdoors, it's not going to bring outside air into your house. Those are the simplest, but they can potentially be the most expensive because there is no heat recovery involved. So it's just as they bring outside air into your house, your conditioned air is also leaving. So the pressure is kind of balanced by the fan that's pulling on it. And so the way to prevent that is to use heat recovery ventilation, a balanced ventilation system. And so what you can see in the bottom right of the screen is a heat recovery ventilation unit. They also come in an energy recovery ventilation unit. That's another variety. The difference in those is that the heat recovery ventilation unit only recovers heat, whereas the energy recovery ventilation unit recovers heat and moisture. That's a little bit potentially beyond the scope of this class, but just to let you know that there's a variety. But essentially what those do is they maintain the balance of pressure in your house. So they're bringing in as much air as they're pushing out of your house. They're passing it through this core in the middle. They're taking advantage of those two air streams crossing each other and siphoning off some of the heat into the oncoming airstream. And then you can also put filters on that to make sure that the outside air that you're bringing into the house is as clean as it can be, because sometimes outdoor air is not necessarily cleaner than your indoor air. And those have the potential, they'll definitely save some heat energy depending on where you live, how cold it is, and installed costs may save you total costs, but certainly on the energy side, they're effective. All right, so getting into the specifics of these. So with any attic insulation project, and we'll kind of think about this in the simplest attic first, which would be a vented attic. And so that would be what people call a cold roof. So the insulation is on top of your house. It's just above, you know, the drywall, the wood, whatever it is, it's right there. And so if you think of the roof itself, you've got all this ventilation and outside air in between those two things. People call that a cold roof. If you've got a cathedral roof or a vaulted ceiling, those tend to be called a hot roof. It can be nuanced, but essentially because the insulation, the roofing, and the interior of the house, they're all kind of sandwiched together, there is the ability for heat to transfer between those. And so that's why they call it a hot roof. But we're going to think of mostly in a vented attic sense for this one, because it tends to be the simplest, kind of the most ubiquitous. You'll see them everywhere. And essentially, with most insulation projects, you want to do air sealing as part of the project, because if you don't, air that moves through that assembly will kind of reduce some of the impact of the insulation as it goes in there. So you may think that you've added R20 insulation, which tends to be a great kind of catch-all number for supplementing what you already have. But if you haven't addressed any of the air leaks, you may be wondering, how effective was that insulation that I just put up there? So you've got to combine those two things together to actually kind of realize the comfort and energy savings that can be done with that. And so that's really just about thinking about the existing attic. You know, how can you access it if it is a cathedral roof? Like, can you pull the existing insulation out? Is it probably simpler just to wait? Do you have a re-roofing job coming in your future? Maybe wait 5 years, do that all at the same time and address those together. So you just got to think about the specifics of your house with that, but more often than not, this tends to be one of the less expensive approaches with the most bangs for your buck as far as energy efficiency retrofits goes. And I guess I will mention, if you live in a coastal area, so here in Fairbanks, people use cellulose a lot in their vented attics for a variety of different reasons, but you do want to think about the type of materials that you're putting in assemblies that are exposed to outdoor air, especially if they're exposed to wet outdoor air. So if you're out on the coast, you might want to think about the differences between going to a material that's not going to degrade with moisture, such as mineral wool, fiberglass, things like that, that tend to be moisture resilient. Looks like I got a quick question that I'll handle before we go into crawl spaces about roofs. So basically, if you've got what's called a hot roof, so if you've got a cathedral roof, the only way to get more insulation in there is to come at it from the inside or the outside. So you're either gonna lose some ceiling height, or you're gonna add on to the roof. Ultimately, approaching it from like the bottom of the house, trying to insulate in any sort of fashion up the roof line, it's really not going to work. You've got to kind of go wholesale at it from either below or above. And most people probably don't have a deep enough framing in their roof to really make it worth their while. So if you're going to re-roof, like that's your chance to make for deeper studs or do continuous insulation on the top and really kind of augment that assembly. So with crawl spaces, so if we think of the house kind of acting like a chimney, we just took care of the top part of the chimney, so really reduce the amount of air that's going through our house. As Ness mentioned, with hot air rising, we're kind of just capping that off with air sealing and insulation. And then likewise, the bottom of the house is going to also be a really weak point for us. And so if we're thinking about a crawl space, we want to make it nice, comfortable, conditioned space, not living space comfortable, but comfortable enough that you'd go crawl around there if you wanted to. And so what that means is putting in a vapor retarder that's rated to actually make sure that the moisture does not intrude into the space. And you want to make sure that that is air sealed and secured to the wall. So it's going to do a couple things. It's going to help keep soil gases, i.e. radon, from coming into your house, but the main thing is it's keeping moisture out, but it'll also reduce air leakage. So it kind of does all of those things all at the same time. And you really just want to make sure that you've lapped all your joints, sealed everything correctly, and secured it in a way so that, 2 years time, you don't go down there and you see that it's fallen off the wall because I used the cheapest duct tape I could find at the box store. So you really want to put a lot of effort into it. And you generally want to go with at least R10 insulation. So whatever insulating method you're going for, as with most things, you want to put enough insulation there to make it worth your while. And then as you've closed the space in, so we've tightened everything up, there may be the chance that maybe you've got lots of plumbing and things down there, something that's introducing more moisture into the space than is really just being naturally ventilated out. You might have to mechanically ventilate the space or dehumidify the space. So if you're in a, say, Juneau with a partially below grade crawl space, it's probably going to be fairly humid, more humid than a crawl space would be, say, in Fairbanks. But ultimately, you have to get that moisture out and keep it below 60% relative humidity is generally a good reference point. We can go to the next one. All right, so kind of going back to the ventilation aspect. So we've handled our attic, we've handled our crawl space. So now we're thinking about what can we do from a ventilation standpoint, just thinking about the best possible method. So you've decided, I don't want to just operate a bath fan anymore. I'm tired of depressurizing my house. Cold drafts that come in, so we're going to handle it with balanced ventilation. So that would be the heat recovery system or the energy recovery system that we mentioned earlier. And similar to what we mentioned with heat pumps, where it's essentially you got to kind of diagnose the existing conditions of your house and then build out your strategy from there. It's similar with ventilation. You need to understand how big is your house? How many bedrooms are there? How close are you to your neighbors? Are you running combustion appliances on one side of the house and you've got kitchen exhaust on one side of the house and a door on the other? You got to think about where you're pulling in your outside air, where you're exhausting your air to. And so you can generally reference some above code programs, which would be the Energy Star residential program, or you can go, if you're in a municipality that has a building code, obviously reference their code. If you don't live in a municipality with a code, you can go to the International Residential Code and use the code as a reference. It's a good starting point. Doesn't tend to include most of the best practices. And then in thinking about the HRV, where we're going to put it, it is, a decent sized appliance. They're fairly small, but they've got to go somewhere, especially if you want to keep the ductwork in the conditioned space. A lot of people like to put them in the crawl space or even the garage. If you've just, made your crawl space super nice and fancy, air sealed and insulated, that's probably a good place for it. If you have not done that, that's not a good place for it. And likewise, a garage tends to not be a great place because if you look at the bottom right, that box of the HRV tends to not be completely airtight. And so if you think about what you put in your garage, maybe you store your weed whacker in there, lawnmower, things that you used all summer long to keep your lawn looking nice, and now you're parking the car in there in the winter. There tends to be a lot of things that put out compounds in the air that we don't necessarily want to be breathing in the house. So generally recommend to not have it in the garage. Do want to be considerate of, where are the duct runs going? At the end of the day, it's balancing act of where can I put this appliance? Where can I put all the duct work? So you kind of have to work with what you've got as far as your existing location goes. As with ductless heat pumps, we kind of want to consider the floor plan. So when we're thinking about where we're running the ductwork, can the air travel between the spaces? Ventilation systems are all about return air pathways. So essentially, if you put some air into a bedroom and somebody closes the bedroom door at night, is the undercut of the door adequate enough to allow air to kind of go back in between? If you've ever gone to work at an office and maybe 4 people sit in a room, you close the door and within a few minutes it gets really hot in there, it's because everybody's breathing in there and there's not a good return air pathway. So you kind of want to keep that same concept in your house. And some other things to think about are, do you have other fans in your house? Are you going to continue to use them in that manner? Do you want to use them for ventilation? HRVs do make condensate, so you kind of want to keep them near a drain line. Think about filtration. So all of that is to kind of say, you do have to do a little bit of education as you think about, is this a good fit for my home? Where's it going to go? And how am I going to maintain it? Because as with a lot of mechanical systems, if you don't maintain it, if you don't clean the filters, you don't clean the core, it's not going to work as you hoped it would. And then similar to heat pumps, they've been making a lot of strides lately as far as cold climate technologies and applicability. So they work at colder and colder temperatures and they work more efficiently at colder temperatures. But you do have to do a little bit of research, make sure it's a unit that's supposed to work at the temperatures that you're dealing with. You can buy a relatively inexpensive unit, but it might not operate exactly as you hoped it would. All right, so that's still me. So all that's being said is how do we figure out all of this? So, not everybody wants to get in their attic, get in the crawl space, take some measurements, do all of this stuff. If you can do all that, and that's great. Most people tend to be pretty, I guess, enterprising in Alaska and willing to take on projects themselves. But ultimately, hiring a professional is a great way to go about it. So it's good idea to get an energy audit. So to get somebody to come out to your house, they'll look at everything and they'll take all the information, all the existing specifications of your house. So insulation in your attic, double pane windows, triple pane windows, what kind of door do you have? How big's your house? What's in your crawl space? All of that goes into what's called an energy model. And the conventional energy model in Alaska is called AK Warm or AC Warm, depending on who you talk to, and that's administered by the Alaska Housing Finance Corporation. And so that's really nice common language if you're aware of the star rating systems that are developed from the Acorn software. So when people start talking about 6-star homes, 5-star homes, 2-star homes, really it's just all kind of putting homes on a similar baseline and being able to gauge the energy efficiency of them. And so if you get an energy auditor to come out to your house, they'll do an envelope leakage test. And so if you look in that picture, there's a red door with a fan in it. They'll stick that in your door, they'll suck all the air out of the house, and they'll measure the leakage rate. And that's really important for determining how efficient your house is at coldest temperatures, because you'll really start to lose a lot of air at really cold temperatures, and that's when you really need that air. And so that auditor will be able to take all that information, plug it into the energy model, and then get those design loads for your house. And really that's the type of information that will help you determine, is a heat pump a good fit for your house? Do you need to make some upgrades on your house before you consider a heat pump? Maybe heat pumps aren't even on the table. You just want to be aware of how your house is operating. I've got a boiler. I just put it in 2 years ago. I'm not losing it for like 6 more years. They'll take a look at that. They'll make sure it's operating in a safe manner in your house. So it doesn't all have to be striving towards swapping out what you have. It can be about maximizing what you currently have in your house. And then we mentioned on the other slide the Desire database, but there's some in-state rebates and financing available. There's what's called the 45L tax credit, which is totally geared towards new construction, but essentially you kind of have to be able to track and benchmark either your existing house or your potential new house before you even start to understand, are you available to get rebates or financing for the work you're doing.
Okay,
All right,
it's
that's
back to
you,
me.
Ness.
Sorry. I had my mouse on the thing to click the slides over. I was just realizing while you were talking, Connor, there's always something I want to edit on slides before I send them out. And we don't have a link to AK Warm, which is that energy modeling software that energy auditors in Alaska use on here, but I will include that. I'll go ahead and put that link in this presentation because it is free. And if you are somewhat familiar with computers and construction, that is something you can do yourself. So energy audits are a couple $100 and usually well worth the money because they do give you a list of the highest payback efficiency options for your house. But if it is something that you would really enjoy digging into yourself, you can download that software and see all the fields that you need to fill out, gather that information about your own house, and then start playing around with what could potential retrofits look like, and how much could they reduce your energy cost. That being said, the slide has a list of resources. We'll send this out afterwards, so you don't have to be hurriedly writing them down. Just different resources for information about building that same website again, the Desire database. Just because if you are looking at a particular retrofit, you can go to the Alaska state on that one, get a list of potential incentives or rebates that might be out there. I haven't read the chat since break, but I did notice that somebody had put in there about the Bristol Bay campus. They offer a lot of free classes that go beyond the level of, the ones that CCHRC is offering, like this 2-hour one. I think they have like a 4 to 6 hour class on heat pumps that's coming up. So it's being taught by Chandler Kemp, who's actually an energy auditor, former energy auditor as well, who has a lot of experience with heat pumps, and he'll have time to dig a little bit more into the details for that. And yeah, if you take enough of those classes, you can get your sustainable energy occupational endorsement too. So yeah, bonus. That kind of wraps us up. For those of you that are here for the CEUs, Till at CCHRC will be emailing those out. So if you haven't received it, and it's a person doing this, and she kind of has to go through the roster. She has to match up names with the people who had originally like checked the box wanting a CEU and then, you know, email them out. So it doesn't happen like instantaneously. But if you haven't received it in about 2 weeks, you might want to reach out. Or if when you signed up for the class, you didn't check the box for CEUs, but you decided you wanted CEUs, Till would be the person to ask about that. So her email address is there. And then I have all of our emails on this site. If you have questions and you didn't think of them tonight or we didn't get to them tonight, please feel free to contact any of us. And if that person can't answer your question, we'll share it amongst ourselves until we figure out which one of us or another person that we can refer you to. So I am going to see if there are any questions in the chat. And then also, I think we have one more poll of just, yeah, again, anything you answer on the polls really helps CCHRC to offer and information insights to offer good classes in the future.
Yes, I do just want to flag, there are 2 questions that weren't addressed in the chat. They're just to expand a little bit on the question from Gregory from Bristol Bay, specifically asking about if there's anybody in Alaska capable to price and install a system in rural Alaska. So I don't know if you can see that in the chat. It looks like he's writing a grant, so wanted to know.
Let me read this.
I think it'll be easier for you to read it than me reading it to you. It's a little longer.
Yeah, oh, too cool. Okay. So we are not allowed to recommend contractors, but right now I'm trying to think of any that I would even know. Yeah, I guess first of all, I have to say that anything that comes out of my mouth in the next 10 minutes or Conor, like it's not a recommendation. The second part is you should always get multiple quotes, assuming there are multiple people that would even quote this. This sounds really cool. Conor, who did Bruno used to work for? Trying to think of who would do this.
Yeah. So, sorry if you can hear my dog barking. Essentially, this is likely not going to be a single contractor. So solar and batteries might be one contractor. Heat pumps will come from a different contractor. Lower 48, you'll see a lot of electric companies are starting to install mini splits because they tend to, especially in the colder states, most people are doing a panel upgrade at the same time. But likely, you definitely, as Ness said, want to kind of follow the traditional like government procurement style of getting 3 bids for each style of service. Potentially reaching out to Alaska Housing Finance Corporation, see who's working in out of Anchorage and like traveling out to the rural areas. So like for Fairbanks, heat pump installs are not really common enough that people are like leaving Fairbanks to install them in the rest of the state. And then the fact that we're based up here makes us a little bit behind the curve on knowing contractors in Anchorage. So I'd probably start making some calls that way and just trying to work out a list.
Yeah, and if this is in Lower Bristol Bay, I mean, maybe you're already in touch with the UAF Bristol Bay campus, but yeah, like Conor was mentioning with the heat pump installers, there's really not a lot of heat pump installers in Anchorage, which is probably where you would think you would get a contractor out there for this, just because Anchorage has natural gas, so it does make the economics of heat pumps a little harder. But you might be able to find a heat pump installer that could come do this installation, and then at the same time, maybe like teach a class at Bristol Bay. That way kind of get paid for the trip in 2 ways. In terms of the solar systems, you might reach out to the Solarize campaigns, probably in the Anchorage area, because they would be more familiar with the solar installers down there. And I would think you'd probably be looking at a solar installer coming out of Anchorage rather than Fairbanks, since it's one less flight to get on. Did we miss another? I gotta scroll up, Carrie.
Looks like there's a question about if the downtown power plant could extract enough heat from the Chena River for its distributed heat system. So most of our focus is residential. So I'm gonna, go out on a little bit of a stretch here for an industrial application, but I'm gonna assume at this point, probably not. I think given, how much the Chena freezes up, that's probably gonna be an issue as far as, needing heat when you need it the most, i.e. January, February. Most of the heat pumps that are put into water tend to be in like warm bodies of water. So that's why the Sea Alaska heat pump, is in a relatively warm bay as far as like water goes. And if you see people who've got ground source heat pumps that they put in their ponds, tends to be in areas where the pond is deep enough to where that water is staying, nice and warm at the bottom. But there's all sorts of considerations, and I have not a great sense on the entire load of the downtown district heat system to know what the capacity is.
Yeah, thank you to the person, Mr. Berger, that put the Acorn download link. So I'll add that to the PowerPoint too, but yeah, that software is free to download. So
yeah, and
decently
on that,
intuitive. So we work in buildings, so there's that, but I don't think it's that hard to figure out. And if you have questions, you can call us.
It's good to play around with, good to get an idea. If you're pretty familiar with, the bills of your house, so that's an easy way to kind of true up the model. You know how much you're spending on your own house. So if you make a model that says you're only using 100 gallons of fuel, but you paid for 500 last year, go back to the drawing board on that. Do want to say using Acorn is useful to understand, potential upgrades to your house, but in order to qualify for any rebates or anything like that, it has to come from a certified auditor. So somebody who is professionally licensed to do that. So just be aware of that you're not going to be able to present your own certificate to some governing body and qualify for rebates.
Let's see. Well, if no one else has questions, you know how to find us. So if you think of one later, feel free to email, and we will definitely track down and answer for you. And otherwise, Carrie or Mindy, did you guys have anything else?
I do not.
Mindy's in the building with me, and her dog came to visit. So anyway. All right. Well, I think good night, everyone. Thank you for coming, and many thanks to our sponsors and then CCHRC and Information Insights for facilitating this one.
Thank you.
Thanks, Carrie.
Yeah, thanks, Mindy. I wasn't sure if you had anything last minute, but I was just want to let you know, I'll make sure that I'll get everything sent out tomorrow to all the attendees. And then I will send you, because I've been thinking about that for the CEUs, I'll make sure that you get the Excel file of all the participants as well. I'm assuming that will help.
Yeah,
with
that'd
that.
be great.
Okay. Do you want me to just email you, or?
Email me and Till, because
Okay.
Till's doing that.
That's right. Perfect.
Thank you.
Awesome. Thanks, Mindy. Have a good night.
Yeah, bye.
Bye.